Hello everyone. In this video we'll go over some of the software that we're going to be using in week 3 and week 4 of the semester, which will be going into the IDEA laboratory using the fabrication and mechatronics resources. So some of our objectives for this particular video is to talk about some of the computer-aided manufacturing software that we're going to be using in these weeks, as well as mechatronics programming environments. We'll talk about some of the process workflow that we have for some of the fabrication methods that we'll be using in laser cutting and 3D printing, how to generate CAM files for fabrication, which are going to be important for some of the task sheets that you have for the training requirements, as well as some of the installation details and where you can find that information for the software packages. So we have a few different software packages that we're going to be using here. The first is Solidworks, and many of you have already been exposed to Solidworks in your prior coursework. Solidworks will be used to create a couple of different files, DXF files that we use for laser cutting, STL files that are used for 3D printing. You can access SolidWorks either on your personal computer or using the resources available through MyCloud, which is our VLab resource, the virtual machine resource. We also use Inkscape, which is used for preparing files for laser cutting. You can install Inkscape on either your Mac or on a Windows PC. There's also Trotec Job Control. This is used for controlling the laser cutter in the IDEA lab. This can only be installed on Windows PCs. If you do not have a Windows PC, you'll be able to use the resources in the IDEA laboratory to use job control. We will be using Cura, which is a 3D printing software. It's used for creating G-code for 3D printing from CAD files. That can be installed on either a Mac or a PC. Additionally, we're going to be using the Arduino IDE. That's the programming environment for the Arduino. That can be installed on either a Mac or PC. And then lastly, GitHub is an online repository that we'll be using that has some of the libraries for the mechatronics kit that we have in this particular course. The freeware that you'll be able to download, these are the Arduino IDE, Cura, and Inkscape. Trotec Job Control, I have some instructions there. You can access it using some serial numbers that we're providing, and SolidWorks you can download from OIT. So just some word on different kinds of formats. DXF files are these 2D layout files that we have that are used to control which way the laser will go and to assign parameters to cuts and various other kinds of features that we'll be using in laser cutting. STL files are 3D files that are tessellated surfaces that you use for producing 3D printed parts. Other kinds of file formats that you're going to run into in this next several weeks are SVG files, which are Inkscape files that are used to save the layouts for a particular file. We have 3MF files, which are the Cura files that are the G-code that you use for 3D printing. And then you have PJX files, which are the files that have some of the commands for the laser cutter embedded in them. And those are used for Trotec Job Control. Laser cutting is a laser-based material removal method. Many of you might be familiar with it if you've used the resources in the Invention Studio. There are a couple of different operations that you can do on a laser cutter. You can do cutting versus engraving. And that's just the difference between how deep the mark is made on the laser. If it's all the way through the part, then you're going to be cutting that part. It's a 2D manufacturing process, so these are used on sheets of material. There are some limitations in the types of materials that you can process using this approach and within our laboratory, and you'll get trained on that as you get into the training weeks in the IDEA lab. You use computer-aided manufacturing software to drive this kind of machine, and that's what we'll be talking about here. And in this class, we're limiting you to MDF kinds of materials at 1/4 inch thickness. The process workflow for laser cutting is as follows. You see here, you start with a CAD file, could be in SolidWorks or another type of drafting system, and you output a DXF file, which is that 2D layout file. You open up that file in Inkscape, which is the software we're talking about, and then you use that and you send it using a printing command to Trotec Job Control, and then that can be used to assign machine control kind of instructions. The Inkscape file itself can be saved as an SVG, and the Trotec Job Control file can be saved as a PJX so that you can archive that. When you're setting your laser cutting parameters, it's important to note that how you set these parameters have a strong influence on the result on the material and the quality of the process. There are three primary parameters that we can control on this machine, that being the speed of the laser, which is how fast the laser is moving left to right across the part, the power of the laser, which controls the intensity of the laser on the part, and then finally the number of passes that the laser goes over a particular line that it's meant to traverse in its trajectory. These three combinations of parameters we adjust to get good-looking cuts in terms of the amount of time it is required to remove parts, as well as the quality of the surface in terms of what is its visual appearance, as well as whether or not it actually achieved the operation that we wanted to achieve, whether it be cutting or engraving. 3D printing is, many of you are also familiar with 3D printing. We're going to be using Ultimaker 2 Pluses in this laboratory, which are fused deposition modeling machines where you have a filament of material that you're melting onto a build plate and building up parts layer by layer. It's a 2.5D manufacturing process, meaning that you are primarily using XY for your primary axis, and then it moves up and down to give you that third dimension of control. Again, here we also are using computer-aided manufacturing software, which is Cura, and there are some limitations in terms of geometry that you can produce using 3D printing. This in particular looking at the size, obviously the size of the parts that you're making, as well as some of the constraints that you have from the standpoint of support structures and things of that sort. In this class, we have filament that we're providing free to all of you to use within the time budget that you have available week to week. And there we have PLA and PHA type materials. This is the process workflow that we have for this particular approach. You start with Solidworks or another CAD file. From there you can produce an STL file that you can import into Cura. There you generate G-code that you upload to an SD card and load that on the Ultimaker 2 Plus to actually print the part. You can save your Cura files as a 3MF file for archiving that information. Just as in laser cutting, there are also parameters within 3D printing that control some of the performance measures that you might be interested in. Here you see some examples of different parameters and how they affect the print itself. Controlling things like infill changes the amount of material that is being built within a part, within the surfaces that would not be of interest to the overall user. You also have layer thickness, which changes how much vertical movement it's using between steps. Support structures, which are used to provide support to gravity to these molten beads that are being laid down. Bed adhesion, which changes the nature of the bottom of the part and how that's attached to the build plate. Are you building a larger pad compared to the part? We also have bed temperature and nozzle temperature, which are used to change the thermal conditions on the build plate or at the nozzle. All of these parameters have an influence on quality in terms of the geometry that you see. So if you have the incorrect settings for parameters, you might not get good bed adhesion, you might not get good overall geometry relative to the part that you wanted to achieve. There also is some performance differences in terms of material usage. As you can tell with the infill density changing, you might be depositing more material, and whether or not that is important or not is dependent on what your objectives are for your particular design. We also have time changes, so the more material you're putting down, generally the more time it's going to take. So the first software that we have is SolidWorks. Many of you have used SolidWorks in prior classes in 1770. And for SolidWorks, the most important thing that we want to get across is you can use SolidWorks as a way of creating the files required for laser cutting. So the first thing to think about is when you're looking at the workflow for SolidWorks, you'll be opening up files that have been modeled, perhaps by your team members or by some other person that you might be working with. And what you want to be able to do is output a DXF file and STL file. So now I'll show you how to save a DXF file for laser cutting and an STL file for 3D printing using SolidWorks. So the first thing we have to do is download the files that you're going to be using for this studio. If you go to the Studio Material Schedule tab under the ME2110 website, there are files here that you can download for this week 3 and week 4 training. Clicking on this link will give you a Dropbox location where you can download these files. There will be two folders here that you can save. One is the 3D printing file, which is a bushing that we're going to be printing using the Ultimakers. And then the other is the laser cutting files, which we'll be using the Trotec Job Control for. So here, if you click on this link here, you'll see the chassis that we're going to be producing, which you can use for your robots later on. Here we're going to be laser cutting the side panels as well as the platforms out using the laser cutter. So after downloading these files, you can open up the side panel in Solidworks, and this is what it will look like. And from here, what you need to generate is a DXF file that shows this panel for the laser cutter. The way to do that is to click on the face that you want to create the DXF file for. If you right-click here and go to Export DXF DWG, this will open up a dialog box that you can use to save that view as a DXF file. So here I can save the DXF file by hitting save. And then on the left side of the screen, there will be a dialog box asking you some information that it wants to save that file. We've already selected the face, so that's already selected here. I can hit save and it will generate that file. And there you see the overall layout. So next, we'll save an STL file for 3D printing using SolidWorks. If you open up the bushing file that was provided on the ME2110 website, this is what that part looks like. To save an STL file, it's fairly straightforward. You go to File, Save As, and from there you can save it as an STL file. So here I can download or I can select the STL setting for Save As type and save that file. Okay, so the next thing that we'll talk about is Inkscape. Inkscape is software that we use to prepare files for sending these to the laser cutter after they've been output as DXFs. Here we'll open up a DXF, we'll modify the colors on that DXF so that we can assign laser parameters to those colors so that we can produce, for example, cut pieces. That's the workflow that we have for Inkscape. From there we will be printing the files and sending that print to Trotec Job Control, and that's where we can actually run the parts on the machine and assign settings directly to particular colors that have been set in Inkscape. So in terms of installing Inkscape, we have on the ME2110 website installation instructions for installing that. I refer you to look at that. Those installation instructions will inform you how to modify the color palette as well as screen zoom settings so that you get the best possible outcomes when you're preparing your files. You'll want your color palette to look like the one that you see here in the bottom of this screenshot. This is the one that's native to Trotec Job Control and is different than the one that comes pre-installed with Inkscape. And that is all described on the ME2110 website's installation instructions. So in Inkscape, we're going to be doing the following. We're going to be loading DXF files and making sure that they can be on top of the right sizes for pages so that when we print those pages that they open up in Trotec Job Control accurately. We wanted to delete any annotations that are not relatively important for the actual laser cutting process. A common annotation that we'll have to remove is the actual footer that says educational version for SolidWorks. And from there are different kinds of operations. One is a fill operation, one's a stroke operation, and we're going to be modifying these depending on what we're trying to achieve. After we do that, the last thing to do in Inkscape is to show you how to export files using the save function to save files as an SVG format, which can be opened in other computers, as well as sending jobs to our laser control software, which is Job Control. And from there, we're going to do various steps, including modifying print settings like you see here in these screenshots. So first we'll go over to Inkscape. After you install Inkscape and do the required operations to upload the templates and the color palette, this is what it should look like for you. We have here the rough sizing of the print bed, which is 29 by 17, as well as the palette of colors that are common to Job Control. So this is what your environment should look like once you've installed Inkscape. So we'll open up the DXF file that we had saved in the previous step. And you have a couple different options here when you're importing it. You'll want to read from file for the scaling so that it brings in the dimensions that were from the Solidworks file. So in doing that, this is what it should look like. So if you can scroll out, you see here we have our file. This is the canvas for this particular drawing, and this is the file that was imported. If you hold Shift, Control, and R, it should adjust the canvas accordingly to fit your for your part. In this case, the side panel for that drawing. There's a couple of things that we'll do here. First thing we'll do is delete the annotations that are unnecessary. You can click here on the individual text boxes for the watermark that's associated with the SolidWorks educational product. And then at least for this particular file, that's all you'll need to do. I'll resize again the canvas to fit this drawing. Shift, Control, and R, and that will bring the right dimensions in here. So the first thing that we're going to do is we're going to modify the colors on this particular drawing because the colors that we'll use in Job Control will be used to set laser parameters as well as the trajectories for the laser. So in this case, all of these features, these holes, which are mounting holes, as well as these slots here, are all going to be cut out using the laser. So I need to assign these to a red color. If I do Control A, which is to select all features on the component, I can select all of the lines that I'll have to change the color for. And then I'm going to change these to red. And we're going to be using what's called a stroke operation. A stroke operation is one where we assign the boundary or the perimeter of these shapes to a particular color. So I'm going to, just reading from the bottom menu here, use Shift click to set the stroke on these parts. And now you see here that I've assigned all of these features to a red color. You can also do a fill operation, which would be used for different purposes that we won't be going over here at the moment. So now that I've saved, now that I've assigned the color red to these particular features, the next thing to do is to export this to Job Control and to save it to an SVG file. So we'll do that. To save this as an SVG file, you go to File, Save As, and you can save this as any number of different files. Here we'll save it as an SVG so that we can open it later on another computer. So that's covering saving of this particular file. Now to send the information or the file itself to Job Control, we're going to use the print function. After you follow the steps to do that on your computer, you'll be able to see here in the printer options, you'll have a selection for Trotec Engraver. If we go here to Preferences, what you'll see here are a couple other pieces of information that are important for exporting your file to Job Control. A couple things to note here: make sure to set your user-defined size as 29 by 17, which is the bed size for the laser cutter. Minimize the job size is important because that will minimize the overall print to the size of the actual drawing that you're sending from Inkscape. And that should be all that you need for this particular operation. This button here stores the settings, and next I can do is print and send this to Job Control. So now if we go over to Job Control, this is what the Job Control software looks like. You see here we have a file that says print side panel.svg, which is the file that we'll be using in this particular exercise. So in Job Control, what we'll be talking about is the workflow for using this software. So we first send jobs to Job Control using Inkscape, as we just saw here. From there, we will lay out those jobs onto the printer plate. Here, this center portion of the screen. We will then assign laser cut parameters to those drawings, and that will be the instruction set for the laser cutter to actually produce our components following those trajectories. We'll talk about how do you optimize those jobs, save those files, and then actually run the laser cutter itself. We'll talk about connections to the laser system using this software, as well as management of the job queue. So what we'll look at next is we'll talk about positioning these jobs on the plate here. The size of the laser cutting bed is about 29 by 17 inches. And you see here, this is what it would look like when you lay out components. Because this is a nozzle, a laser cutting nozzle that's traversing a linear distance, the closer that you can make the components that you're using with the laser cutter to each other, the amount of time that you'll spend traversing the laser across the build plate will be minimized, and that will reduce your actual time using the components. And that's important because each team will have a limited budget available for using the laser cutter during the week. We'll talk about the actual power and cut settings, which are, you see here in the above that layout. You see here, these are settings that can be set by the user, and we have some recommended settings that you'll use for the MDF parts that you'll be using in training, as well as some operations that you could use to optimize your cutting paths to minimize the time required, and then how do you actually estimate the time associated with your jobs. So if we go back to the Trotec Job Control, we see here the same environment that we saw in those screenshots. I can drag my parts onto the laser cutting plate by selecting them and dragging them here. You see here, this brings the component onto the build plate, and we have here the same colors that we've assigned in the Inkscape software, in this case red, which will be attributing to the paths for the laser cutter. In some cases, this view doesn't come in directly. Sometimes this is what you'll see on your screens. If you select this eyeball, this will provide a direct visualization or preview of the components as they will be laser cut. So if I select the actual drawing, you'll see a couple of other things come up here on this left menu, including for the cut parameters or the cut settings, what is the time associated with actually doing the cutting operations for that particular color, as well as information on how much time is going to be required to actually cut it following those pre-programmed laser cutting parameters. So in many cases, you'll have to modify the actual laser cut parameters. If you go here to Material Templates and you click on that, you see here that we can modify a couple of different parameters here, the power, the speed, the number of passes, and these are going to be important. In many cases, you'll be able to rely on the path parameters that we've identified for the material systems that we have, that you'll be able to use that for your actual prints. So you can update that, and I'll just put in an arbitrary number here. If I increase the speed, you should see that after I update this will reduce the time required to make your components. The challenge is that what are the right parameters to use here, and we do recommend that you use the recommended parameters that we have. So a couple other things to note here is that you have a couple other options here in the menus. This is one interesting feature called vector ordering, and this is to optimize the actual sequence of trajectories that the laser will follow during the cutting process. There's a couple of options like a quick ordering of those vectors, as well as an enhanced ordering, which follows a genetic algorithm style approach to optimize your paths. Here I'll just do a quick ordering, and we'll see how that changes this time. So if I update that, you see here I have a slightly lower time than I did to begin with, and that's how you might be able to optimize your jobs. As I said, you can lay out more parts here. If you send more jobs from Inkscape to Job Control, they should show up here as different files, and you'll just drag them onto your build plate and try and minimize the footprint that they take up to optimize your time and your material usage. The last thing to consider here is to save your files as a PJX file. Here, you can do that, and this way you can archive this for later use if you need to. So that's the laser cutter. The next thing to talk about is 3D printing and Cura. So Cura is the software that is made by Ultimaker that we'll be using for driving the 3D printers in the IDEA laboratory. The workflow for this particular piece of equipment and software is to load the STL files that you'd save using Solidworks or using another solid modeling program, open that up in Cura, and then assign parameters for the 3D printing process. We talked about different parameters including infill, support structures, bed adhesion, layer thicknesses. These change the quality of your print as well as the time required to print your components. So from there, you'll change those parameters in the Ultimaker Cura software, and then you can either save the file as it's configured, or you can actually create what's called G code to actually drive the machines. So you'll save that in Cura, the G code, and then you'll upload that to the printer using an SD card. So in the we'll open up that environment here in a second, talk about how you set those machine configurations, how you open STL files. We'll also talk about how you do different operations on the build plate, how you actually drop components onto the build plate, how do you do a couple of different operations like move them, scale them, rotate them, multiply them, mirror them, and arrange them to get the best possible outcomes for your print. And then adjusting print parameters is something that we'll do using these menus. And then within the Cura software, you can save the project files so that you can open them in another computer or later on, and that is a 3MF format. And then finally, creating the actual machine instruction set for the actual 3D printers. We'll also talk about how do you preview your builds, and here you see an example of the preview. You can actually see the support structures as they will be printed for the part, as well as the use of any rafts or bed adhesion. And then you can also get time and material estimates here before you create the G code. And then here you see on the right and the bottom the sliders that you can use to actually preview your components. So when you open up the Cura software, this is what you'll see on your computers. Here you see we selected the Ultimaker 2 Plus, which is the style of 3D printer that we have in the Ideal laboratory. Some other parameters, including the filament that we're using and the diameter. And then here are settings that could be modified based on the actual layer heights that you'd like. Here, this is the profile setting, which changes the layer height. Infill setting, which changes the actual density of the print within the structure. The use of support structures, as well as the use of bed adhesion. So bed adhesion is the use of rafts, for example, which increase the anchoring of the print to the build plate. You also have ability to set more custom settings that you see here, or you can set these general parameters themselves. So the first thing to do is to open up the part that we will be using for the training session. That would be the bushing file. And the first thing that you'll note here is that the actual part is not laid out in the ideal orientation on the build plate, because this would require the use of support structures due to the angular constraints for the printing process. So the first thing to do is orient this so that its axis is pointed vertically on the part. So we can do that using the rotate function here. And if I select a face to align to the build plate itself, I can select this face right here and it would change the orientation of the part. This menu also provides a couple of other options. You could move the actual part on the build plate. You could scale the part if you want by changing that there, and it by default uses uniform scaling. You can rotate the part. This is an axisymmetric part, so if I rotate it in plane, it won't really have any impact. I can mirror these parts as well as change some other settings that you can investigate on your own as you wish. Another thing that you can do in Cura is you can create multiple models. So if you wanted to bring in, say, 4 other copies of this part, you could do that here, and it would mirror. It would actually drop them onto the build plate automatically. Another thing that you might want to do is actually make sure that the process takes as little time as possible. And if you have a part, say, on one side of the build plate, one challenge you might have is that the nozzle has to go to one side of the build plate and then back to this side. So there's this function called arrange all models that allows you to minimize the travel required for that 3D printer. From there, you can do a couple things. You could save this project file if you want, and that'll save it as a 3MF file so that you can perhaps upload that later or open up on another computer with your team members. We can also then create G code that can be driving the Ultimaker itself. So this slice function is basically the operation that is used to create that G code. So in doing this, it'll create an instruction set, which is an NC code that we will upload to the printer directly. This gives a couple of options that you want to pay attention to here. First, you see here already a time estimate that's provided for this job, 4 hours and 18 minutes, as well as a material usage. So this can be used for time and material estimates as you're preparing for manufacturing your components. We can also preview this job if we want. And you see here, we can look step by step in the build process to visualize what is happening at various moments in time. From there, you can also investigate different layers using this slider here. We can then save this file to an NC code. This G code is what will be used to upload to the 3D printers. This will be saved to an SD card. We'll take that SD card out and then bring it to the 3D printer for printing. So that covers the 3D printing portion of the software that we'll be using, as well as all the software that we'll be using for the fabrication in terms of the use of Solidworks, use of the Trotec Job Control, Inkscape, and Cura. The last piece of software that we will be using is the Arduino IDE, and you can consult the ME2110 website for instructions on how to download the Arduino IDE. We'll spend some time during training on how to program in that environment and upload your code to the Arduino microcontroller. So with that, that's all we have to talk about today. We look forward to seeing you in studio.